In this segment, we're going to learn about free radicals. We're going to start with the definition of what is a free radical, give some examples of free radicals, and then we're going to look at applications of free radicals toward the field of organic chemistry. So for that, we're specifically going to be focusing on the general structures of carbon radicals that we will encounter. After we finish this segment, we will then go into reactions in organic chemistry that involve free radicals. So first off, we need to get the definition out of the way and what we're referring to when we talk about a radical, or also known as a free radical. Whenever we're talking about a radical or a free radical, what we're referring to is a molecule that has, or an ion, that has one or more unpaired electrons within the molecule. So by definition, a free radical is going to be referring to a molecule or an ion or an atom, for that matter, with unpaired electrons. So typically up until this point, we have generally looked at electrons occurring in pairs. A lone pair of electrons is a very common thing to see. Less commonly, we will see instances where a molecule has an unpaired electron. An example of this that is relevant in industry and medicine is the example of nitric oxide, NO. So if we were to draw out the Lewis structure for NO, what we would find is that we have an odd number of electrons. And when we have an odd number of electrons, that means there has to be an unpaired electron somewhere in that molecule. So we're going to draw out the Lewis structure that exists for NO, which is this structure right here. For NO, there's also a second resonance structure, which we can indicate with this resonance arrow. And the second resonance structure of NO, nitric oxide, will look like this. The resonance structure on the left would be considered the major contributing resonance structure due to the fact that it has no formal charges on either of the atoms, whereas the structure on the right does. A fun factoid about nitric oxide is that in the year 1998, it was declared as the molecule of the year because of the discovery of its role as a cardiovascular signaling molecule. It is, like most other free radicals, a relatively unstable molecule, so it's present in the body only transiently, but while it's transiently present, it is responsible for regulating vasodilation and hence regulates blood pressure as a result of that. So it certainly has a really prominent role in physiology and medicine. Another example of where free radicals come into play in real life is in the environment. So the ozone layer destruction that you may have heard of as a result of a group of molecules called chlorofluorocarbons, where chlorofluorocarbons, or CFC, refers to molecules that have chlorine atoms, fluorine atoms, and carbons. And what happens is that when those are exposed to the UV light that is in the upper layers of the atmosphere, that UV light triggers the breakage of bonds to chlorine to release chlorine radicals. And those chlorine radicals then are very unstable, very reactive, and they react with the ozone. And hence, by reacting with the ozone, they are destroying the ozone layer. And that's why chlorofluorocarbons, or CFCs for short, have been banned from use as refrigerants. They were once really common as refrigerants, but since then, for the most part, those have been eliminated from the market. So what we're going to focus on next is examples of carbon radicals. Carbon radicals are going to be important intermediates in chemical reactions. Like the other types of radicals that we've talked about so far, carbon radicals are generally going to be relatively unstable. So these aren't molecules that you would typically be able to isolate and identify and use directly for practical applications. Instead, they are going to be intermediates that are present transiently along the pathway from a starting material to a reaction product. And later on, what we're going to be looking at in the next unit is reactions that involve carbon radicals as intermediates. And so first off, we need to understand a few things about carbon radicals and what their roles are and their structures and things of that sort. So we're going to look at carbon radicals. And just as was the case above with free radicals. Our free radical hallmark is that the molecule has to have an unpaired electron. So an unpaired electron there or an unpaired electron here would constitute both of those nitric oxide resonance structures as free radicals. In the case of carbon radicals, what we're going to see is that the carbon atom has an unpaired electron. So an example of a carbon radical would be if we created this structure CH3, CH, CH3, and then we put a free radical there at that central carbon. So if we take a look at that central carbon, we would describe that carbon as being a free radical carbon because it has that unpaired electron that we're showing as a dot there. And we can calculate the formal charge on that carbon. This would be a good chance to hit pause and review that you know how to calculate formal charges on atoms. So we're going to calculate the formal charge here, and the formal charge is equal to the column that that atom is in the periodic table, which is column number 4, minus the number of lone pair or unpaired electrons. So that's going to be 1 because we have that 1 free radical electron, minus the number of covalent bonds. And the number of covalent bonds there is going to be 3 because there are 2 bonds that connect that central carbon to other carbons, and then it also has that hydrogen that is directly bonded to that carbon as well. So our formal charge here is 0, but still, due to the fact that there is that unpaired electron, this is a relatively unstable carbon, or a carbon radical is the term that we can use to describe this carbon that has an unpaired electron. There are, when we think about alkyl radicals, remember that an alkyl group is a group that has just carbon-carbon single bonds. So when we're talking about alkyl radicals, we can break alkyl radicals into 3 basic categories. Those 3 basic categories are going to be primary, secondary, and tertiary alkyl radicals. Remember that alkyl is describing a group that has just carbon-carbon single bonds in it. And of course the hydrogen's required there as well. So much like an alkyl branch coming off of a chain when we were talking about nomenclature refers to a group that has just carbon-carbon single bonds, alkyl radicals are going to be molecules that have a free radical carbon and just carbon-carbon single bonds present there. So the 3 types of alkyl radicals that we will mention and that you should be able to recognize are going to be the primary, secondary, and tertiary radicals. And these are relevant to be able to recognize because these 3 types of radicals are going to have quite different stabilities. And when they have different stabilities, that's going to imply that some of them will form more easily as intermediates during chemical reactions. Some of them will be really difficult or impossible to form as intermediates in chemical reactions. So those 3 types: primary alkyl radical, is going to refer to the situation where the carbon that is a radical has just 1 direct bond to another carbon atom. So an example of this would be if we had CH2 with a radical on that carbon, CH3. So the carbon there on your left, that is our radical carbon, has only 1 direct bond to another carbon atom. So that's why it's constituted as a primary radical. So there's only 1 bond between the carbon that's the radical and another carbon. And that doesn't imply that this molecule can have just 2 carbon atoms in total. It could certainly have far more than 2 carbon atoms. What it implies is that the particular carbon atom that has the radical on it is directly bonded to only 1 other carbon atom. So for example here, we could have a long chain of carbon atoms, and the carbon on the far left there that is our radical carbon would still be a primary carbon radical because it's only directly bonded to 1 other carbon atom. Going down the list, a secondary carbon radical or a secondary alkyl radical is going to refer to the situation where we have a carbon radical that's directly bonded to 2 other carbon atoms, hence secondary radical. So this is going to be our secondary alkyl radical. And our secondary alkyl radical, by definition, is going to have 2 bonds that directly link the carbon radical to the rest, to other carbons. So 2 bonds between the carbon radical and another carbon. Remember that those 2 bonds have to be 2 separate bonds because of the fact that we were calling these alkyl radicals, and alkyl radicals have just carbon-carbon single bonds going on. So a secondary alkyl radical would be something like having CH, and then we have the CH has a radical on it, then we have a carbon chain here, carbon chain off to the other side of it, like so, and the carbon that I'm going to highlight here, that's your radical carbon because it's the one that has the unpaired electrons. And it would be classified as a secondary radical because it is directly bonded to just two other carbon atoms. It's directly bonded to the carbon atom in green here and directly bonded to the carbon atom in green here. We can also write these out as line angle formula. And so to make a line angle formula radical, we have in this chain 5 carbons. So I'm going to make a 5 carbon chain here with my line angle formula. So there's my 5 carbons. And at carbon number 3 of the chain is where we have the radical, and so that's where I need to put the red dot in place, or whatever color dot you're using. I'm choosing to use red there. So that dot there indicates that that carbon has an unpaired electron. Then we go onward, and the third type of alkyl radical is the tertiary alkyl radical, so 3rd degree alkyl radical, and you probably guessed it, that implies that there's 3 bonds between the carbon radical and other carbon atoms. So this is referring to a carbon radical that's directly bonded to 3 other carbon atoms. So we'll say that there's 3 bonds between the radical carbon and other carbon atoms. So we can do an example of a tertiary alkyl radical. So we'll go ahead and put in our carbon, and I have to draw 3 direct links to other carbon atoms. So we could do CH2, CH3, CH2, CH3 as an example, CH2, CH3. And so this carbon here in the middle, put a radical on there. That is definitely a tertiary carbon radical because that carbon that we've highlighted in yellow there, that's our radical, is directly bonded to 3 other carbon atoms. And there's a few additional ways that we could write this out. We could write it out if we wanted as carbon with our radical on it, and then since we have 3 identical groups directly bonded to that same carbon, we could put CH2, CH3 in parentheses, and then subscript 3 to indicate that those 3 ethyl groups are directly bonded to the radical. We could also do this as a line angle formula. So our line angle formula is going to have 3 ethyl branches coming off of a single carbon, and that's carbon is going to be our radical right there that I've put the dot on to indicate that that is our carbon radical directly bonded to 3 CH2 groups. So that's going to be our tertiary radical. One thing that we need to keep in mind and think about here as we talk about these 3 types of radicals, primary, secondary, and tertiary, is the relative stabilities of these. Because the more stable a radical, the more favorable it will be as an intermediate in a reaction. So generally when we do chemical reactions, one of the things we're going to think about is what intermediates lead us from the starting material that we begin the reaction with to the final product that we're interested in. And as we think about what intermediates are favorable, one of the key things we're going to think about is the stability of those intermediates, where generally the more stable intermediates are going to be the more favorable intermediates in chemical reactions. And so we can rank the stabilities of these 3 types of alkyl radicals. When we rank the stabilities of the 3 types of alkyl radicals, what we're going to find is that the order of stability for alkyl radicals is that tertiary radicals are the most stable, followed by secondary radicals, followed by primary radicals are the least stable. So we're looking at stability of alkyl radicals, and we're just going to put a ranked order here, where tertiary radicals are the most stable, secondary are second most stable, primary are the least stable. So our tertiary carbon radicals in reactions are going to tend to be the most stable. They're going to tend to form the fastest in chemical reactions because of that stability. And when we say that something's really stable, by definition, what that implies, that by saying that it's the most stable, is that it is the lowest in energy. And we're going to tend in these reaction types to take the path of least resistance, meaning the lowest energy pathway. And so generally, when we're looking at chemical reactions, we'll see situations where we could hypothetically create a tertiary carbon radical, a secondary carbon radical, or primary carbon radical intermediate. Generally, if we can create a tertiary carbon radical, that's going to be the favorable route to go because those are the most stable. So why is it the case that a tertiary carbon radical is more stable than a secondary or a primary carbon radical? That's a key question to answer here. And it's going to allow us to use some of the terminology and definitions that we talked about previously when we were referring to the stability of resonance structures. So, why is a tertiary carbon radical more stable than a secondary or a primary? So the answer to this question has to do with what factors will enable the stabilization of the radical. Because if we center in on a tertiary carbon radical, secondary carbon radical, and primary carbon radical, the unstable point of each of those molecules is the radical position. And so factors that stabilize that radical position are going to act to create a molecule that's more stable as a whole. So if we have a tertiary carbon radical, such as this structure on the left, versus a secondary carbon radical, the structure that I'm showing here in the middle, versus the structure that I'm going to show on the right, which is our primary carbon radical example. When we think about the unstable portion of that molecule, the unstable portion of that molecule, of course, is the carbon that has that unpaired electron. When we think about whether that carbon atom is electron-rich or electron-poor, we would describe that carbon as being electron-poor. It is lacking a complete octet. It is short electrons, and so that is an electron-poor region of the molecule in each of these cases. And anything that we can do to reduce the poverty of that carbon atom, so to make it less electron-poor, is going to improve the stability of that molecule. We can improve the stability of electron-poor groups by placing electron-donating groups nearby. So electron-poor groups, and this is going to be true not only of radicals but also of carbocations, positively charged carbons, meaning that the carbon doesn't have a complete octet and instead has a positive formal charge. So electron-poor atoms, as a general rule, can be stabilized by electron-donating groups. And hopefully the term electron-donating groups rings a little bit of a bell for you, because back when we were talking about resonance structures and what will stabilize molecules through resonance was that we could have groups that would donate electrons. And one of the ways that they could donate electrons was through resonance. Another way was that they could donate electrons through induction. And we talked about induction as a factor that would stabilize or destabilize molecules when we were referring to the stability of acids and bases, or conjugate acids and conjugate bases. So electron-poor atoms can be stabilized by electron-donating groups, because electron-donating groups are going to tend to shuttle electron density away from themselves and push it toward the rest of the molecule. They're going to try to push it toward the electron-poor atom, which really wants and needs that electron density. So electron-donating groups, there's two ways that groups can be donated, that electrons can be donated. Those two ways that electrons can be donated that we'll focus on here are going to be induction. And remember that we could think of that as a long-distance polarization of bonds, where groups like alkyl groups tend to be electron donating by induction. They tend to push electron density away from themselves and toward the rest of the molecule. On the other hand, electronegative atoms, such as halogens, tend to be electron withdrawing. They tend to pull electron density away from the rest of the molecule and toward themselves. So groups can be electron donating by induction. An example of a group that donates electrons by induction is going to be alkyl groups. So alkyl groups will tend to push electron density away from themselves by polarization of those bonds to donate electron density toward the rest of the molecule. So alkyl groups donate electron density by induction. Another way that electron-poor atoms can be stabilized using electron donating groups is by using electron donation through resonance. And electron donation through resonance requires that you be able to write out a resonance structure that shows that you're moving electron density from one region of the molecule that's electron rich to another region of the molecule that's electron poor. So resonance is going to require the pushing of electrons or the movement of electrons to write Lewis structures that show electron density moving toward the electron-poor atom. So we're going to require the movement of electrons toward the electron-poor atom. And so if you could draw a second resonance structure that showed electron density moving toward the free radical location, that is going to indicate that electrons are being donated and the molecule is being stabilized by resonance. So we need, in order to evaluate why the tertiary carbon radical is more stable than the secondary carbon radical or the primary carbon radical, we need to look at what factors we have here to stabilize or destabilize. So by induction, electron donating groups such as alkyl groups are going to stabilize electron-poor atoms. Resonance, if we can move electron density toward the radical, is also going to stabilize it. So looking at these factors, resonance is generally the most important, so we'll look at that first. With the three alkyl groups that we have up top here, there are no resonance structures that you could draw for any of these three that wouldn't end up exceeding the octet rule. So resonance is off the table here because remember that resonance requires that you move pi bonds or electrons that are not part of bonds, so unpaired electrons or lone pairs. And we only have one unpaired electron here. We have no pi bonds, so we have nothing to move within this molecule because any movement of that unpaired electron is going to end up going over the octet rule for some atom in the molecule. We can never go over the octet rule in resonance. So we're left with induction as the only way to stabilize this molecule. And when we take a look at the tertiary carbon radical, what we see is that we have three electron donating groups that are directly bonded to the electron-poor radical. So we have the methyl group, and methyl group. And alkyl groups in general are electron donating. So we have three electron donating groups here at our tertiary carbon radical. And those three electron donating groups I'm showing in yellow, so I'm just going to put in the key here, yellow equals electron donating group. So we have three electron donating groups there. If we come over to our secondary carbon radical, directly bonded, we have CH3 and a CH3. Both of those are electron donating groups. So we have just two electron donating groups in a secondary radical. And the hydrogen that's there also directly bonded to the radical, that CH group in the middle. The hydrogen is actually slightly electron withdrawing, but it's a very small atom, so its effect is generally really small. But certainly it is not going to stabilize that molecule because it is not going to donate electron density through induction. Then we come over to the primary carbon radical, and in the primary carbon radical we have just one electron donating group, that CH3 group. And so as we go from tertiary to secondary to primary, we're decreasing the number of electron donating groups in each of those cases, and therefore the molecule is being destabilized as we go from tertiary to secondary to primary. So tertiary has the most electron donation and primary has the least electron donation because it has the fewest number of alkyl groups bonded there. So the reason that a tertiary carbon is the most stable goes entirely with this concept of induction, that those alkyl groups are electron donating by induction, and so the more of those you have, the more that electron-poor carbon radical is going to be. Now what we'll look at is a situation where resonance can come into play to act to stabilize carbon radicals. And the case where resonance can come into play is the situation where we have what we refer to as an allylic radical. So an allylic radical is going to be a radical that is separated by a single bond from an alkene group, a carbon-carbon double bond. So an allylic radical has to have the general structure of having a carbon radical that's separated by a single bond from an alkene group. So the general template for an allylic radical is this, which we've written in blue here. We refer to the carbon atom that's connected by a single bond to that carbon-carbon double bond group as the allylic carbon. So we refer to this as the allylic position or the allylic carbon. And the allylic carbon is a really prominent place for radicals to form because of the fact that that radical can be stabilized by resonance. So we can actually physically show that we can share that radical over two different carbon atoms by resonance. So allylic radicals are going to be very stable because they are stabilized by resonance. And remember that resonance is a more important factor, a stronger factor for stabilizing molecules than induction, because resonance physically allows you to fully move electrons from one location in the molecule to another. And so allylic radicals are going to be even more stable than those alkyl radicals that we looked at a little bit earlier. So stabilized by resonance, and as a result, these are generally going to be very stable, still not stable enough to exist for long periods of time, but they are going to form readily within chemical reactions because of the stability. So they're going to be present as intermediates pretty readily. So we can show the second resonance structure for an allylic radical by using some electron pushing arrows here. So our electron pushing arrow, we can take that unpaired electron. Our goal here when we're stabilizing by resonance is to be able to share that radical over multiple atoms so that the burden of that is not stuck on just the carbon atom, but is shared over multiple atoms. So we bring the radical over to here to start making a carbon-carbon double bond. In order to make a carbon-carbon double bond, we can't leave that unpaired electron stranded there somewhere in the middle of a covalent bond. It has to team up with some other electron, and it can grab that other electron from this pi bond over here. One of those two electrons comes over. And by the way, a really important point here is that when we're drawing electron pushing arrows for radicals, to show the movement of one electron, you show a single-headed arrow. So this type of arrow shows the movement of one electron. So it is really important when you're making the electron pushing arrow maps, which is one of the central things that will be done when we get to looking at chemical reactions in detail, is that whenever you're showing a radical reaction or radical process, you move one electron at a time by using a single-headed arrow. On the other hand, a double-headed arrow indicates the movement of two electrons. So back to drawing the resonance structure here, we took and we moved the unpaired electron over into the adjacent bond. In order to do that, we had to bring an electron from the pi bond over here. Pi bond electrons are fair game to move in resonance, so we moved that over one spot. So as a result of this, we're going to have a carbon-carbon double bond connecting the two carbons on the left. That leaves, though, one electron here in the covalent bond on your right, and that unpaired leftover electron has to go somewhere, has to land on an atom, so it's going to land on that adjacent carbon atom right there. So we'll go ahead and write out the second resonance structure here. And by the way, when you're drawing a allylic radical resonance, it is always going to follow this template that we've drawn out here. So you're always going to be sharing that radical over two different atoms. We're sharing it, in this case, over that carbon atom on the far left and the carbon atom on the far right. So neither of those two carbon atoms take the full burden of instability of having a radical on them. Instead, that instability is split over two atoms, so it lightens the load for either of those two carbons and therefore greatly stabilizes this molecule, making allylic radicals more stable even than tertiary radicals generally. So let's take a look at an example problem to wrap up here of drawing the resonance structure for a second radical. So we're going to look at this particular radical, and we're going to ask what additional resonance structure or structures can we draw for that. And we're going to follow the template that we saw up top here, where what we're going to do is we take that unpaired electron, and it's always going to come over one spot to here in order to start making a covalent bond. And in order to finish off that covalent bond, you have to take another electron from the pi bond here and move that over. So now you see two single-headed arrows both coming into that bond. That indicates that you will end up with a double bond located there. You have one electron left in the pi bond right here, and that comes over and lands on the atom adjacent to it to give you an unpaired electron there. And you'll notice that the general flow and template that we're using here is exactly what we saw up top. We've just added some extra atoms into the mix to make things a little more realistic in terms of what you would actually be seeing in real life molecules. So the unpaired electron ends up coming over to here, and our pi bond is going to be right here as a result of those electron pushing arrows. So we now have two different resonance structures, and these two different resonance structures would represent intermediates in chemical reactions. Keep in mind that even though allylic radicals are the most stable of the carbon radical types we've talked about, they still are not super duper stable, and so they still are not something that you would see lingering around forever to be isolated and identified and used for a lot of practical applications. Instead, they are intermediates that form along the route to something that is a more stable final product where the octet rule is filled for all of the carbon atoms. So with that, in the next unit, what we will look at is applying these concepts of the stability of different free radical carbons toward chemical reactions that involve alkyl radicals.